Hello, everybody. I'd like to welcome you to this session called Designing Cooler Cities. My name is Vivek Shandas. I use he, him, his pronouns, and this is an extraordinary time to be having this discussion. In part because, like many other presentations during this event, we've seen the real effects in many parts of the Northern Hemisphere of a very intense summer. Whether you're hailing from the East Coast, Southern California, the Northwest, the Midwest, or the South, it's really a time for us to be having this conversation about what it takes to make our cities a little bit more cooler, or maybe a lot more cooler and more habitable for everybody. So I'm delighted. I've been working in the field of climate adaptation for about 15 years, and I serve as a professor at Portland State University. And much of what we've been having conversations about this summer after the Pacific heat dome descended upon us has really been apropos for this particular conversation we're having today. So I'm delighted to be able to welcome you all and really get us started in terms of the this event. I'd like to really start by thanking a number of the sponsors, as you may have heard already in different parts of the event so far. This is a group of folks who've come together who see the writing on the wall that much of what we've experienced, not only this summer, but throughout the year, are telltale signs of a changing climate and something that we really need to be getting in front of, particularly in places where more people live than any other part of the planet in these cities. So really grateful for these sponsors. I'd like to, before turning it over to the speakers, I'd really like to give you a sense that we're really asking you to put all your questions into the Q&A option that you have, and you can go ahead and put those questions in after each presenter sets up their presentation, completes it. We're going to move on to the next. We're going to move on to the questions discussion for that particular presenter, and then move to the next presentation. Each presentation is about 20 minutes, and we're leaving about 5 minutes for questions and discussion. So without further ado, let me just give you an idea of who you're here, who you've probably seen this already, but I'm delighted to have with us Aldo, Brandi, Edith de Guzman, and Kelly Turner. They come from a variety of different backgrounds and really presenting everything from human experience of thermal comfort to numerical modeling simulations. And so really quite a rich and robust discussion for us today. So I'm going to go ahead and introduce Aldo as the first speaker. And I will simply say that Aldo, I'm getting to know Aldo through this event, and I understand I'd like to introduce him as somebody who comes from Bari, South Italy, or as I think they may say, Bari, Southern Italy. And he has a bachelor's and a master's in geological and geophysical sciences, and has been really working to improve his knowledge about atmospheric sciences and defining the skills as an instructor. And so he's pursuing his PhD at Arizona State University as a candidate now, and currently explores the interactions between urban environments, climate change, with a focus on boundary layer dynamics, particularly in cities. So I'll go ahead and turn it over to you, Aldo, and we can go ahead and get started.
Thank you, Vivek, for your presentation, and good afternoon, everybody. Today I will share with you some findings from my most recent work addressing the potential impacts that projected climate change, urban development, and heat adaptation strategies are expected to have on the urban boundary layer of cities of the Conterminous United States at the end of the 21st century. The atmosphere is almost completely transparent to solar radiation, whose most energy is contained in the shortwave portion of the electromagnetic spectrum. The atmosphere takes almost all its thermal energy from the interaction between the long-wave radiation emitted by the Earth's surface and the greenhouse gases in the atmosphere that absorb and remit it. Accordingly, the air that lies closer to the Earth's surface becomes warmer and less dense than air at upper levels, and thus tends to rise because of its buoyancy, transferring heat vertically in the atmosphere in a process called convection. The ensemble of convective and radiative heat transfers from the surface to the atmosphere is called sensible heat flux and contributes to the formation of the planetary boundary layer, which is dominated by turbulence and convective mixing. The depth of this layer, its vertical extent, depends on convective mixing intensity and is then used as a proxy variable to describe boundary layer dynamics. For example, in this schematic, we can see how the boundary layer depth reaches its maximum shortly after noontime when solar radiation is at its peak, and it shrinks down at nighttime when it's only sustained by wind-produced turbulence. Since the onset of the industrial era, atmospheric concentration of greenhouse gases like carbon dioxide and methane has been increasing as a consequence of fossil fuel combustion. As a result, more of the energy emitted by the Earth's surface is absorbed, and the overall thermal energy of the atmosphere increases, leading to higher temperatures. Such an energy excess also provides additional fuel to a series of atmospheric processes whose intensity, length, and recurrence frequency is increased. Examples are hurricanes, wildfires, and heat waves. In this figure, from a recent paper by Broadbent et al., we can see on the left panel how downscaling climate modeling expects urban development and climate change to increase the number of hot days contributing to heat waves for all US climate regions, thus increasing also the amount of population exposed to extreme heat, as shown in the right panel of the figure. Urban populations are especially exposed to this extreme heat as, in addition to climate change, they dwell in environments characterized by additional heat sources like transportation vehicles, air conditioning systems, and paved surfaces like tar and concrete that absorb more solar radiation than their natural counterparts. All of these sources fall under the umbrella of anthropogenic heat, meaning heat produced by humans. Nowadays, urban-related heat exposure affects a considerable amount of people, as more than half of the world population already lives in urban environments, and their share is projected to grow even more in the future. Addressing the global causes of climate change entails reducing greenhouse gases emission, which in turn requires a series of globally coordinated efforts that are financially and structurally difficult to implement. Luckily, as our next speakers will tell you in more detail, there are actions that can be taken at the local level to adjust to climate change and reduce or avoid harm to populations. Adaptation to global warming and extreme heat in urban environments is mostly pursued through attempts at reducing the amount of solar radiation absorbed by paved surfaces like roads and building walls and roofs, by increasing their reflectivity, as well as using evapotranspiration processes of plants to convert part of the sensible heat into latent heat. Commonly proposed heat adaptation strategies include cool roofs and white roads to increase the reflectivity of paved surfaces, green roofs to shelter buildings with plants that use solar radiation for their biological activities, and street trees that provide a combination of shading and evapotranspiration. However, anthropogenic heat is not the only problem affecting urban environments, as some of its sources, like transportation, heating systems of buildings, and factories, also emit polluting chemicals in the atmosphere. Now, if you recall our initial discourse on surface heat and convection, you can anticipate how reducing surface heat will decrease convective mixing. If you think of the planetary boundary layer as a pot on a stove that is filled with boiling water, you can expect that reducing the burning strength will reduce boiling intensity and convection inside the pot. Since the majority of pollutants are emitted near the surface, a lack of convection-driven vertical mixing can lead to worse air quality at pedestrian level, where most humans live and breathe. Many of you may be familiar with this landscape and with the depiction of what weak convection can mean in densely populated and highly polluted environments. So, let's have a closer look at the physical processes that take place in developing urban environments affected by climate change when heat adaptation strategies are implemented. The amount of anthropogenic heat sources plus the heat absorbed by paved surfaces of cities both participate in increasing sensible heat in urban environments. The imbalance of impervious surfaces reduces the amount of soil that can get wet by precipitation, thus decreasing latent heat. And in addition, the three-dimensional morphology of urban environments interacts with solar radiation and winds, trapping heat inside urban canyons. This leads to urban boundary layers that are deeper and more mixed than their rural counterparts, as additional heat and physical obstacles contributes to turbulence production. So, what should we expect to happen to urban boundary layer dynamics when we implement heat adaptation in cities? More precisely, how will air quality be affected by the implementation of measures designed to improve thermal comfort in urban environments? My research team and I tried to answer these questions through numerical climate modeling, and we recently published the results of our work in a peer-reviewed paper in the Climate Dynamics journal. We focused our analysis on the Conterminous United States, and we first analyzed regional impacts across the entire country. Then we selected 8 case study cities from different climate regions and with different projected growth rates to look at differences in local impacts. We first performed control simulations for both contemporary and projected urban development and future climate scenarios. Then we performed a suite of sensitivity experiments to take into account individual and combined impacts of uniform and extensive implementation of cool roofs, green roofs, and street trees. More details on these simulations can be found in a paper by Krayanov et al. Published in Nature in 2018, and all simulation data are freely available on the ASU Dataverse Research Data Repository. Okay, so we first examined the regional impacts of urban development intended as both urban expansion and densification on urban boundary layer depth, both in a contemporary climate, left side of the figure, and in a projected end of century climate, on the right side. Urban development is expected to increase urban boundary layer depth by tens of meters, especially in the eastern, more humid part of the country, where urbanization increases the abundance of paved impervious surfaces. Climate change is expected to exacerbate urban development impacts on urban boundary layer depth, as both drivers result in sensible heat increase and latent heat decrease. The only exception to this trend is represented by Central California, where urban development entails a transition from arid to urban landscape that increases the amount of heat stored in surface materials. We can then conclude that urban development and climate change are expected to increase urban boundary layer depth, both individually and combined. But what happens if we add heat adaptation to these scenarios? Simulation results show that each of the considered adaptation strategies is expected to decrease urban boundary layer depth by several tens of meters, while the simultaneous implementation of all 3 adaptation strategies, a scenario here referred to as full adaptation, is expected to produce up to a few hundred meters reduction of urban boundary layer depth as a consequence of sensible heat decrease. Furthermore, heat adaptation strategies are expected to increase latent heat flux as a consequence of added vegetation to the urban landscape, whereas we found no potential impacts for ground heat absorption. If we look at local impacts for the 8 selected case study cities, we see that individual impacts of urban development and climate change sum linearly when considered simultaneously, and together can increase urban boundary layer depth by several tens of meters. Full adaptation implementation is expected to completely offset such increase and produce a further urban boundary layer depth reduction of a few hundred meters. Additionally, impacts from all drivers, and especially from heat adaptation, are stronger inland areas and weaker on coastal cities. We get then to our second takeaway, that is that heat adaptation strategies are expected to strongly reduce boundary layer depth in urban environments. But let's go deeper. The boundary layer depth reduction is a consequence of decreased convective mixing, which means that the lower atmosphere becomes more stable. In this figure are represented vertical profiles of potential temperature differences between no adaptation and full adaptation scenarios for the New York City and the Los Angeles and San Diego metropolitan areas. Potential temperature is a thermal quantity of air masses that is conserved through pressure changes that do not involve exchange of heat, and it is used as a proxy variable for atmospheric static stability. In this figure, we see that all heat adaptation strategies reduce potential temperature in the urban boundary layer, both in New York and in Southern California, thus suppressing vertical motion and mixing, making the atmosphere more stable and less turbulent. However, we can see that despite a potential temperature reduction near the surface in Los Angeles and San Diego half a degree greater than in New York, the vertical extent of full adaptation impacts on potential temperature is more than 700 meters lower in Southern California than in New York City. Although not shown here, similar impacts are found for the nighttime boundary layer in terms of static stability, and I refer you to our climate dynamics paper for more details and figures. So, we got to our third takeaway on the potential impacts of heat adaptation and urban boundary layer dynamics, which is that heat adaptation is expected to increase static stability in the urban boundary layer, both at daytime and nighttime. However, we wanted to further investigate the difference in the vertical extent of heat adaptation impacts for New York and Southern California. So we analyzed annual average composites of urban boundary layer depth and heat flux differences between no adaptation and full adaptation scenarios for the two considered conurbations. In this time series, we see that the urban boundary layer depth reduction, the blue line in the top panel, average over the metropolitan areas of Los Angeles and San Diego, remains more or less constant around minus 100 meters throughout the year, despite a reduction in sensible heat flux, the magenta line in the bottom panel, that shows a clear seasonal trend with peak values around minus 160 watts per square meter in late June. We hypothesized that a possible explanation for this discrepancy lies in a similarly timed increase in latent heat flux that, adding moisture to the boundary layer, can decrease its static stability, thus counterbalancing the sensible heat reduction effect. Such a phenomenon is only observed in Southern California, and our hypothesis needs further investigation to be fully supported. However, a partial confirmation comes from the analysis of the same annual average composite over the New York City metropolitan area. Here, urban boundary layer depth reduction changes through seasons, again the blue line in the top panel, peaking at minus 180 watts per square meter in July, which is almost double the depth reduction in Southern California, despite a summertime sensible heat flux reduction of only 60 watts per square meter, which is less than half of the sensible heat flux reduction over Los Angeles and San Diego metros. Notably, over the New York City, the latent heat flux change remains constant around zero throughout the year. So, despite the need for further and more detailed investigation, we can conclude that background climates affect the way that heat adaptation strategies can impact urban boundary layer dynamics. Now, let's wrap it all up and recall the findings of our work, which are that urban development and climate change are expected to increase urban boundary layer depth by tens of meters, and their impacts are greater in the eastern part of the Conterminous United States. Heat adaptation strategies are expected to offset such increase and further reduce urban boundary layer depth by a few hundred meters. And they're also expected to increase both daytime and nighttime static stability near the surface. Finally, background climates modulate urban development and heat adaptation impacts on urban boundary layer dynamics. For example, heat adaptation impacts are greater inland and weaker over coastal cities, and in Southern California, adaptation-induced latent heat increase may counterbalance sensible heat reduction impacts on the urban boundary layer depth. So what we can grasp is that the interaction between landscape changes and background climate has important consequences on urban boundary layer dynamics. The outcomes that we have just seen, like urban boundary layer depth reduction, increased static stability, and the associated subsidence, entail a downward compression of convective mixing that has the potential for higher pollutant concentration at pedestrian level. With this, we don't want to discourage the implementation of heat adaptation strategies in urban environments, but we want to highlight the need for thorough evaluation of trade-offs between achieving thermal comfort and preserving air quality in urban environments when designing and implementing landscape modifications in a multi-co-benefit perspective. Thank you for your attention, and I will be happy to take any questions.
Thank you, Aldo. I want to open up the floor. It looks like we're getting a few questions coming in. Start with Joshua Applegate's question of what policy at the city, state, and federal levels would influence full adaptation? Maybe start there, and then it gets a little deeper in terms of the price tag per potential degree for full adaptation, and is it feasible for cities to consider full adaptation? So it's a very practical, pragmatic question in terms of, what would it take from a policy point of view, and then the potential cost for it in terms of impact. I don't know if you looked at that, but do you want to try?
Well, I don't think I can answer this question because I focused on the physical processes involved with heat adaptation. What I can, I'm sure that Kelly Turner can answer these questions later because I think that her, the next speaker, both next speakers, I think they talk about policies of heat adaptation. What I can tell that is that we considered the realistic implementation of full adaptation through green roofs that feature plants that have leaves, broad leaves with a high reflectivity that can approximate the values of current implemented cool roofs. So in that sense, full adaptation can be actually implemented in cities, but I have no idea about the costs and the policy hindrances behind this. Sorry.
No problem. Thanks, Aldo. Thanks, Joshua. And if it's the same Joshua I'm working with, hello. Dave has a question. It's unusual to have regional climate simulations for addressing such questions. Can you comment on what advantage is gained from pursuing, say, a short-term WRF run with current and future climate boundary conditions versus longer-term run as you've used? What about aerosols?
Well, the first thing, first of all, thank you, Dave, for this question. And the first thing that comes to my mind is that with the shorter simulations, you could increase the resolution of your modeling design so that you can get like more information on the micro scale and mesoscale. I think that I didn't mention about our simulations that they have a 20-kilometer resolution, which given the regional extent of our domain was like a needed compromise between resolution and length of the simulations in order to preserve computing capabilities. What about aerosols? Well, I don't know because they can definitely affect the amount of solar radiation reaching the surface. But our models only dealt with the physical aspects of like boundary layer dynamics, and there's no chemistry involved in our simulation. So probably that's for sure material for further investigation, further research. Thank you.
Great, thank you. Would you, Aldo, keep going a little bit more and talk about the differences? Kelly Turner's asking differences between latent and sensible heat flux for addressing thermal comfort.
Oh, yeah, sure. So thank you for this question, Kelly, because that's actually an important point because the increase of latent heat, which is entailed with many of the heat adaptation strategies that they talked about, and especially with the full adaptation one, increases the amount of humidity and moisture in the atmosphere, which makes the sweating coping mechanism of our bodies to deal with heat less effective. So that's increasing moisture in the atmosphere and in the boundary layer is definitely detrimental for thermal comfort for humans. because it affects the capacity of our bodies to cool down through sweating. And so, yeah, that's definitely something to take into account also when implementing heat adaptations. I hope that answers your question.
Great.
Thank you.
Thank you, Aldo. Wonderful. I'm wanting to just be conscious of time and just thank you very much, Aldo. If I don't see any other questions coming in, and I'll,
Thank
um,
you for having me.
yeah, excellent. Good luck in wrapping this up, and congratulations on the publications already.
Thank you. Thank you so much.
Excellent. So I'd like to move on to the next presenter, and no, no. I have the good fortune to work with Edith de Guzman on several different fronts. And I first met Edith as a director of research for the Los Angeles-based nonprofit Tree People. Though Edith brings a very deep knowledge to this field because she's investigating some of the best practices for sustainable transformation in the LA region, where her work includes research, demonstration projects, and public planning in urban forestry, heat mitigation, and watershed management. Edith's also the co-founder and co-founded and directs the Los Angeles Urban Cooling Collaborative, which is a multidisciplinary partnership of researchers and practitioners working with communities and governments to design data-driven, inclusive strategies for cooling neighborhoods using trees and highly reflective surfaces. And today, Edith will be talking, and right now, Edith's also a PhD student at UCLA, PhD candidate, it looks like, and I'll be looking forward to, I think we'll all be looking forward to hearing about cooler and healthier, reducing heat health risk using urban forestry and stakeholder engagement. So Edith, wonderful to see you again, and the floor is yours.
Great, thank you so much, Vivek. Let me know if you have any trouble hearing me, but I think I'm on.
Yes, very good.
All right, thanks, Vivek, great. So wonderful. So it's my pleasure really to join a group of such accomplished and inspiring individuals in the session on designing cooler cities. And I feel like I've already learned a lot from Aldo's presentation. Over the next few minutes, I will share a case study from Los Angeles with you, looking at how to reduce heat vulnerability using land cover interventions, some of which Aldo actually described. And specifically, I'll be looking at trees. This will include a bit about the problem of increasing heat, as well as approaches to potentially addressing this issue by engaging community members. It will probably come as no surprise to any of you that heat is a major threat to public health and that low-income communities and communities of color tend to bear the brunt of that problem. This is due in large part to neighborhoods that often have too much opportunity for heat to be produced and retained in and by built surfaces like roads and buildings, and too little opportunity for that heat to be dissipated by trees, plants, shade providing structures, and other mechanisms. And actually, our moderator, Vivek, has made really significant contributions to our understanding of this issue. And I encourage you, I should have put this on the slide, but I didn't. I encourage you to check out an article that he co-authored last year about the legacy of federal housing policies of the last century and what those legacies still kind of how they present themselves on how heat is unevenly experienced in American cities today. LA experienced its hottest day on record almost exactly 1 year ago. It was on September 6th of last year, when the neighborhood of Woodland Hills hit 121 degrees Fahrenheit. My colleagues and I had installed a thermal sensor network in a few homes in Southeast LA. And on that day, one of our study sites hit an indoor temperature of 107.4 degrees. This was in a living room in a duplex that has no air conditioning and where there is virtually no tree cover. And I admit that even I was frankly surprised that we recorded such a high indoor temperature, which is in a critically dangerous threshold because the human body just cannot cope with such prolonged exposure to heat. So what can we do? We know that air conditioning access is very effective at reducing heat risk, but it's also not sustainable in its current form because, first of all, it's unaffordable for many of the most vulnerable residents. And of course, it also contributes to climate changing emissions. So the question we wanted to ask is, are there alterations that we can make to the urban environment that can make a difference? I spoke at this symposium last year and I presented about the first study that my colleagues and I in the Los Angeles Urban Cooling Collaborative conducted. And the collaborative, as Vivek briefly mentioned, has representation from academia, nonprofits, and it's really a national collaborative where we're looking at all parts of the U.S. really focusing on new approaches in LA and sharing that with other regions. So, just very briefly, a recap of that study that I presented at last year, where we did some modeling. Actually, we used WRF modeling. Somebody asked about that in the previous session. We decided to treat Los Angeles like a patient, and in this case, we thought of it as a patient suffering from extreme heat. So we asked, what would we prescribe our patient in order to reduce that heat? So what we did is we tested combinations of low, medium, or high, but still achievable targets. For example, we looked at high albedo or solar reflectance and low tree cover, and we tested these targets against current baseline conditions at the local level. And in all, we looked at a few prescriptions combining different what we called dosages of tree cover and albedo. We used actual meteorological and public health data and modeled how these different prescriptions would do in terms of cooling neighborhoods and in terms of saving lives. And in a very brief nutshell, this is what our research found. In terms of temperature, we found that reductions between 1 and 2 degrees Celsius were common, which may sound small, but it's actually quite sufficient to save lives. We quantified how many lives could be saved and found that under various prescriptions of tree canopy and solar reflectance, reducing heat related deaths by 25% or more was a common outcome, which translates into dozens or potentially hundreds of lives saved in the worst heat waves. We also found that we could change weather situations, which is not something our climatologists often see. What this means is that under some of the prescriptions, certain heat waves were shifted from the more oppressive types of air masses, for example, the one that causes our Southern California Santa Ana winds that are so notorious. And it would shift those oppressive air masses to more benign ones, which can improve public health outcomes greatly. Finally, we also looked at projections and we found that these land cover prescriptions could have a quantifiable benefit on delaying or even negating heat impacts of climate change for the region with the scenarios delaying warming between 2 and 6 decades, depending on the scenario, and locking in relatively cooler temperatures for that period. So the next question really is, these are very encouraging results, but why don't we just plant more trees if trees are a great thing to do or to have to cool cities? And now I will ask Natalie to show a very brief video, about 30-second clip. Natalie, if you wouldn't mind getting that started. Thank you. So take a look at this drone footage of two LA neighborhoods and note the difference in green cover and heat retaining surfaces. Boyle Heights on the left is in a heavily urbanized part of the city with 94% Latino residents, many of whom live under the poverty line. On the right, you see Brentwood, which is predominantly white with household incomes over $100,000 a year. So as you can see, just right off the bat, we already face an uneven distribution of trees versus heat retaining surfaces. And that's even just right in our city, in the same city here. Let's see if there's a way to advance here. Thank you, Natalie, for your help behind the scenes. So that's one challenge. Another challenge we face is that in our region's semi-arid climate in Southern California, we can go 8, sometimes more months out of the year with no rain. Trees that aren't on automatic irrigation lines, therefore, will need to be watered manually for the first few years of their lives until their roots are connected with underground hydrology. And on this slide, I share the tale of two trees planted on the same day in South Los Angeles. The photos show them a couple of years after planting. One is regularly watered and cared for, and the other is not, and I bet you can tell which one is which. I don't know about you, but I would definitely rather be enjoying the shade of the tree on the right on a hot day than on the left. And this is a reality. So we know stewardship is needed. Our changing climate is another challenge. We are seeing a trend toward hotter and drier stretches that are testing even hardy native tree species and their resilience to those conditions. And all of these conditions really make a mix of species in our urban forests to be the equivalent of like a tasty buffet for opportunistic pests that really take advantage of less resilience in the urban forest. And finally, the reality is that it's much easier to secure public funding for planting than it is for the ongoing maintenance and care that's required for them. So, with these challenges in mind, we embarked upon a study funded by the California Department of Forestry and Fire Protection and in partnership with LA based tree people, as well as California State University Northridge and the city of San Fernando, to explore engaging LA residents in caring for the street tree planted just in front of their home. We explored whether tree stewardship engagement programming could also engage residents on the topic of rising heat. And we effectively wanted to move people to better understand and act to protect them and their community during heat waves. We tried both community tailored and more generic approaches, and we tested whether messaging that emphasizes environmental health or public health produced better outcomes. We structured our study using community based social marketing, or CBSM, which is an approach that was developed by environmental psychologist Dr. Doug Mackenzie Moore, which provides an alternative to commonly used approaches of trying to move people to pro environmental behaviors just through awareness raising and communications and information. And there's a growing body of evidence that shows that providing information generally doesn't result in the adoption of environmental or health behaviors. So, CBSM is based on social science research that shows that behavior change can be effectively achieved through initiatives delivered at the community level and focused on removing barriers to an activity while simultaneously enhancing its benefits. And it involves 5 steps that I'll illustrate to you through the next few slides. Our first step was to determine our target audience, which in this case was residents whose home is near a newly planted tree in the city of San Fernando. San Fernando is a small city adjacent to the city of LA, really surrounded by the city of LA in the northeast San Fernando Valley. And it is the traditional, ancestral, and unceded territory of Tongva, Chumash, and other indigenous peoples. We reached out to 400 households in San Fernando and got about 120 of them to participate, which is not too bad given this all happened remotely during the pandemic, which means we couldn't go door to door and had to do everything by mail or email. Caring for a tree includes a few different tasks, and that's what our behavior really was about. And those tasks can range from watering to pruning to weeding. For this study, we wanted to really focus on watering, which is the most important task to ensure that trees would thrive. We knew we needed to be really clear about what we were asking our audience to do, so we provided clear instructions for checking their tree's soil moisture once a week, and if the soil was dry, how to water the tree. These are considered so-called end state and non-divisible behaviors, which basically means that they bring the desired outcome that you want, and they also are based on tasks that are specific and can't really be further broken down. Our next step was to identify what barriers exist in our audience around watering a street tree and simultaneously to understand what benefits people have around the idea of having more tree cover in their neighborhood. We used a combination of information gathering methods to learn what trees that trees essentially they are broadly appreciated for in their environmental and aesthetic value, which is great because that means our program wouldn't have to do a lot to boost benefits of trees. We also learned that barriers to tree care are mostly not structural. In other words, people mostly have access to water with spigots and hoses that can reach the tree, or if they don't, carrying a bucket of water wouldn't be a very difficult task for most respondents. We also learned that two perceptual barriers exist. One that is the perception that it's the city's responsibility to care for trees, even though there isn't always funding. And two, that watering trees could end up being very expensive. So this information armed us with what we needed in order to develop an engagement strategy that would boost benefits and lower barriers to tree stewardship. So the community-based social marketing toolbox has a variety of strategies that are meant to break down those barriers and boost those benefits. And you see some of them here, how we sort of develop strategies around them. So we had instructional pieces, reminders to do a task on a given timeline, and demonstrations of commitment that other neighbors could see so that a social norm could be adopted in the community. We had developed materials for a previous study a few years back in another community in LA, and we decided we'd see how those materials performed compared to materials that we created specifically for the San Fernando community. And those materials were meant to appeal to the high degree of neighborhood pride in San Fernando. So a control group received what we considered a control group received the generic materials in both Spanish and English. And then two other groups got the more community specific materials also in Spanish and English. One of those groups had materials that highlighted the links between trees and improved environmental health, and the other highlighted the links between trees and public health. So, for example, the first one emphasized how trees make the neighborhood cooler, and the second emphasized how trees could help reduce rates of asthma or diabetes or obesity. Each group initially received a packet with a letter explaining the program and with various items that provided that specific instruction. The prompt reminder, the weekly reminder, which was either a car air freshener or a small plant, which needed to be watered weekly, and a static cling commitment sticker to be placed on a street facing window. The environment and public health groups got essentially the same packet with the exception of different messaging. Both of those groups also received two reminder postcards in the mail in the subsequent weeks, which reinforced the messaging that they originally got with the packet. With our program intervention happening, we conducted about 3 months of observation. Our crew went out to the sites weekly to collect soil moisture readings using moisture sensors, and they also collected observations about site conditions and tree health. At the end of the evaluation observations, we conducted a second and final survey to see how resident attitudes and knowledge had changed. And I'll now share some of the preliminary findings about that longitudinal research. The survey had nearly 50 questions, and we're still collecting a few remaining responses, but here are just a few of the findings. We learned that the value that people place on trees grew in the environmental health messaging group. That value is quite high in all groups, regardless, but it actually went down a little bit in control and public health groups, which is perplexing. We also saw that knowledge around the importance of trees to human health grew in all three groups. As well, we saw some unintended consequences. People were generally less willing to pay for watering their tree after the program intervention. It's possible that priorities changed during the course of the pandemic, but it's also possible that the program made people feel more burdened with the responsibility of tree care and perhaps less willing to assume that responsibility. And speaking of responsibility, we saw that people's belief that the city is responsible for tree care was reduced after the program, which is something we were hoping to see. We were also curious to find out where people's locus of responsibility lies. Specifically, we asked residents to let us know whether they think that helping communities prepare for a disaster or an emergency is mainly the government's responsibility, or whether it's everyone's responsibility or their own responsibility. We see somewhat mixed results, with two of the groups moving toward personal responsibility and the public health group actually moving toward government being more responsible. And we asked people both before and after the program which actions, if any, they take to prevent heat-related health problems during heat waves. Actions included things such as staying in the shade, avoiding alcohol, closing curtains or blinds of windows that receive afternoon sun, and checking in on friends and family who are ill or elderly. Here too, we saw mixed results, but we do see more of those preventative actions happening among people who receive the public health messaging, which is encouraging from the standpoint of moving communities toward protecting themselves during heat waves. Our soil moisture readings provided the most objective measure of whether residents were moved to care for trees. And here, people in the environmental health messaging group had higher soil moisture, but to be honest, we did not see soil moisture increasing very much in any of the groups. And by and large, trees are still not receiving the amount of water that they really need in order to thrive. Next, we will move to collect the last of our post-intervention survey data. It was quite a challenge to do everything remotely via mail and email during the pandemic, and we found that people just weren't as responsive as they have been in our past studies when we've been able to go door to door and engage face to face. We just received permission from the institutional review board that oversees research methods to do that door to door research to try to collect the remaining surveys, and we will begin that in a few days. We also want to do another round of soil moisture readings to see how things are going in late summer and even into fall. Once we have all of that information, we will be able to conduct statistical analyses to determine how each of our groups fared, and this will enable us to compare the outcomes of this project with our prior project. Even with more steps to this to finish the study, we can already glean some lessons. The first of these is that not being able to engage communities face to face just makes things more difficult. We see lower response rates even among participants. We see lower levels of commitment. So if we get responses, even in that point, we get less commitment. Secondly, the type of messaging has an impact on specific outcomes, it appears, but no one type of messaging shifts all outcomes in the desired direction, which means that a combination of messaging types may be necessary in future programs. Finally, this research raises questions about whether the assumptions that many municipal and nonprofit tree planting programs make, that residents will take on that responsibility of watering trees, whether that's even reasonable. Even with a concerted effort, we were not able to move people to regularly adopt tree stewardship. And there are a whole host of reasons why this might be the case, but fundamentally, we need to ask whether this assumption is sustainable or whether we just need to lobby for more funding and support to hire crews to care for this increasingly important and life-protecting infrastructure. And with that, thanks kindly for your attention. And if there's a tree that looks thirsty on your street, please go and give it some love.
Excellent. Thank you, Edith. I'd like to open it up to questions for a few minutes here before we move on to our final presenter, Kelly Turner. Any questions for Edith? And as we're waiting, I might just seed. I might try seeding a question related to this, Edith. I'm curious about with your survey results, any sub-demographic analyses you were able to do, and seeing if those patterns kind of played out differently among demographic populations, or whether it's high income, low income, or you were even able to like suss out that level of nuance with 100-ish responses.
Yeah, well, we did collect all of that. I mean, we collect, voluntarily, if people were willing to share demographics of that sort, including how many people live in their home, ethnicity, education. Because we're still, we frankly didn't expect that we would still be collecting data at this phase, but it's just folks have been lagging a little bit. So we haven't run those analyses yet, but that is absolutely part of what we're going to be doing in the future, is trying to figure out how different demographics kind of felt about different aspects of this.
Great, great. And a couple more questions are coming in now. I wanted to ask you a question. It sounds like echoing question from Joshua related to the hesitancy of time. Seems like, is there any literature or research, even yours, that you have come across in terms of the hesitancy of time when it comes to tree maintenance, and also the idea that bigger trees might require more time and might create a greater hesitancy, is what I'm inferring from this question. So, how can communities encourage and offset this hesitancy from your work? Any thoughts on that?
I'm not, I'm looking at Joshua's question now, and I'm not completely clear on what he means by hesitancy.
I think it's the like level of effort required, is my interpretation. Level of effort required to take care of a tree adequately, and whether that poses a high enough hurdle for people to just hold off from doing something like maintaining.
Yeah. Yeah, so I think that's the simplicity and the beauty of doing something that that involves community-based social marketing, which we used, really breaks these things down. So it can feel very overwhelming to ask, an individual to improve the urban forest. What does that mean? But if you break it down to something very specific, like the tree right in front of your home, and just check once a week if it needs moisture, if it has soil moisture, if it does not, water it. Here's how you do that. So being very specific with those types of asks is meant to combat that hesitancy, and the idea
Mm,
of understanding barriers that folks have. Are they physical? Are they perceptual? Is also meant to kind of break that down. And I think we're going to have to see how our analysis kind of play out when we're done with the data collection. But I do think that the fact that we're asking folks to do this for street trees right in front of their homes, that's an unclear responsibility. The space of the parkway is not extremely clear, I think. And so I believe the perception of somebody else taking care of it is one that contributes toward that hesitation.
great. And then to continue, Dave has a question around how do you consider the scale of how many trees, where you need them in developing the planting program?
Yeah. Well, I can tell you, I'm not in a position to have to decide that so much, but work with managers in tree planting programs that are in that position. Sometimes it's opportunistic. It's what type of grant you receive, what partnership you're able to forge with the local municipality, and then whether individuals in the community want trees in that particular area or not. How do you consider scale? I mean, more is better, but one tree can also make a big difference on a hot day. So you can get extremely strategic about placement. But actually, some of the work that Vivek and I and some of our colleagues have done around urban forest equity has shown us that actually municipalities aren't terribly strategic about placement in terms of heat mitigation through trees. And so that's actually an area that I think is ripe for a lot more work.
Okay, and really quick, if we can get to maybe one more question that Peggy brings up around, um, is 15 gallons based on a very practical question? Is 15 gallons based on a typical precipitation level calculation? Would you recommend the same level in the Bay Area versus LA?
Great question. So the 15 gallons is something that is kind of a rule of thumb in LA area planting programs, and I actually don't know if Bay Area would be maybe less potentially given their patterns. Um, and I would have to ask specifically how my various colleagues have gotten to this point. But some trees will need less than that, some will need more depending on water demands. But it's kind of a good middle of the road amount that planting programs recommend just for the first 2 to 3 or so years until that tree's roots are connected underground.
Great. Thank you so much, Edith. Look forward to more great work coming from you in the coming months and years. Look forward to working with you as well on addressing some of the questions that have come up today and many others. I
Thanks,
want
Vivek.
Yeah, I want to turn it over to our Final presenter for this afternoon's session on designing cooler cities. I'm delighted to invite Kelly Turner, who serves as the co-director of the Luskin Center, the major event coordinator here today, and is an assistant professor at UCLA. Kelly looks at the relationship between institutions, urban designs, and the environment. Her approach draws from socio-ecological systems framework to address urban planning and design problem domains. Kelly received a PhD in geography from Arizona State University and was an Eigert Fellow in urban ecology there, similar to me at University of Washington. Share that similarity, Kelly. Kelly's also working on as the co-director of this Luskin Center, and I'm looking forward to hearing about hyper-local land systems, synergies, and trade-offs between regional heat island mitigation and pedestrian thermal comfort. So, Kelly, I'll turn the floor over to you.
Right. Can you all hear me?
Yes, very clearly. Great.
Oh, awesome. Thank you. So my title has shifted a little bit. Oh, where's my slides? I see. Apologies. Thank you. Yeah. So thank you so much. First of all, I want to say for everyone, thank you so much for joining us, because I'm wearing sort of two hats here as administrator in Luskin Center, but also as a researcher who studies heat. And, you know, two of the things that during our keynote roundtable that were brought up in terms of the science needs have been addressed already. Aldo, they talked about the need for more work on cascading effects of different climate impacts. And I'm so glad that you are tackling that. And then Edith, there was a lot of conversation about translational science. So thank you all so much. Today, I'm going to be talking about a paper that is currently under review that I have written with a team of folks from UCLA and Arizona State University spanning several different disciplines. And it's the product of several years of work that we've been doing in Tucson, of all places, in a community that was designed to be a new urbanist neighborhood called Savano. And for those who are unfamiliar with new urbanism, it is an architectural school that is interested in creating sort of compact, walkable, and green communities. And that's actually what inspired me to go into to do my PhD work and go into urban planning, was trying to understand from sort of a geographic perspective what we can learn about urban planning and design hypotheses, essentially, about how to make cities more sustainable. Let's see. So there we go. Okay, so for this audience, it's no surprise, cities are hotter because of how we build them, and they could be cooler if we build them differently. And a lot of the narrative around how to cool cities has been informed by, you know, nearly 20, 30 years of regional urban heat island studies that have shown that cities are hotter than proximate undeveloped regions. And so this sort of profile of the city being hotter and the outside kind of hinterlands being cooler is, I think, a shape. This curve is something that we've all sort of been exposed to in the heat world. And the regional urban heat island is super important to address. However, it does direct our attention to certain aspects of urban climate. Specifically, it really focuses our attention on albedo, or how much incoming solar radiation is radiated back out as long wave radiation. It really focuses our attention on surfaces, because the number one thing in all these sort of studies of regional urban heat island that show that if you have high albedo, like white roof surfaces, that you get cooler surface temperatures. And if you have low albedo surfaces like pavement, impervious pavement, you get hotter surfaces. And somewhere in between are grassy, vegetated areas. And so this is focusing, if you can look at this kind of cartoon that I've created here on the the far side, the sunlight, the incoming solar radiation comes in, and if you have a white surface, you get more outgoing long wave radiation, and that's what's going to moderate the regional urban heat island, according to most studies that focus on surface temperature. However, there are other ways to approach urban heat. One of them has to do with human thermal comfort. And so those are the micro conditions that influence the human experience of heat. And they're at a hyper-local scale versus the regional heat island. And human thermal comfort is really an amalgamation of lots of different things. It's influenced by air temperature, it's influenced by humidity and wind speed, it's influenced by surface temperature and the radiant temperature coming off of different surfaces, but also exposure to sunlight. And so, you know, how do we make people cooler? In a nutshell, this is an excerpt from, any of you who remember this book as a kid or have children, this is an excerpt from Go Dog Go, and you see the dog at the top says it's hot out here in the sun, and the dog under the building says it's not hot here under the house because there's no exposure to that direct solar radiation. And so the schemata on the far side with the sun shows that incoming solar radiation, the reason that shade from trees or other surfaces is so effective at increasing thermal comfort is that it prevents solar exposure in the first place. So bodies underneath a tree or underneath another shade structure are not going to be exposed to direct sunlight. And because the surfaces are also not exposed to direct sunlight, then the amount of heat energy radiating back off of surfaces, it's also lesser. So this is why, this is just kind of highlighting the difference between how something like a reflective surface versus shade work in terms of cooling. And in order to understand human thermal comfort, we really need different sorts of measures than just surface temperature. And the probably best approximation for thermal comfort in terms of objective measures is mean radiant temperature. And that just refers to the net thermal exchange between a body and all the objects that surround it. So this study is motivated by the widespread use of surface temperature. So surface temperature is super appealing because it is freely available through satellite imagery. You can get it for almost any place in the US or the world. There are lots of different, you can use products that are free. There are some that you have to pay for, and you can get good temporal coverage because satellites circle the Earth daily and take lots of images, and then you can derive at large spatial extents the estimations of near land surface temperature. So for some cities and for some decision makers, the only tool available is surface temperature because it is such a sort of a simple, relatively simple metric of the climate conditions in a city. But we know from urban climate studies that there are lots of different ways to slice and dice thermal conditions, and there are different temperature metrics. Air temperature we've seen today, and also mean radiant temperatures. So we wanted to ask a question that, is surface temperature a good proxy for thermal comfort? How good is it at predicting how comfortable a person might be, given that many cities might only have surface temperature maps at their disposal? And we looked at a couple different aspects of the problem. One is diurnal variation. How good is surface temperature as a predictor throughout the day? Is it better in the morning or the afternoon or the evening time? Because we know that temperature profiles shift throughout the day. A second aspect of the problem that we looked at is it predicting simulated temperatures? So I'll get into that a little bit more in a couple slides, but is it predicting other measures of temperature compared to using something like solar exposure as your metric? And then also, how does land surface temperature versus other measures, how do they relate to built environment? How do they relate to different land features? So the map here that you're looking at is showing summer land surface temperatures in Tucson. And they're actually a little plug. My newly hired postdoc, Jake D'Alessandro, will be joining us at UCLA, and he created this map for the city of Tucson. And I'll direct your attention to this black box, and this is where our case study neighborhood is located, where you can see that it is a relatively warm land surface temperatures. And the case study neighborhood that we're working in is called Savano. It is it was originally developed as the Tucson Solar Village back in the 1980s. It was conceived of this place that was supposed to harness solar energy and address issues of energy use in Tucson. But it evolved through this public-private relationship and a series of community meetings into a new urbanist, sort of more holistic, sustainable development. And you can see some images here that it kind of draws from traditional architecture and has lots of sort of arid land vegetation. In order to assess temperatures in this community, we used several different approaches. First, we used remote sensing imagery. We used NAPE and Landsat, which are two really relatively commonly used remote sensing products, and we calculated the types of information that would normally be calculated for a city using these products. So land cover, what is the composition and the spatial arrangement of land features. We also calculated LST, or land surface temperature, albedo, that reflection, vegetative cover using something called SAVI as a metric. And we also looked at hotspots for clustering of hot regions versus cool regions in the neighborhood. The second thing we did was some field observations. So we took this MARTI cart, this mobile biometeorology sensor, which was developed by Ariana Medell at the Shade Lab at Arizona State University. And MARTI basically simulates the human body moving out throughout a neighborhood and can measure the exposure to solar radiation and shade and radiant heat coming off of surface, wind speed, humidity, lots of different factors. And we did transects, so loops around the neighborhood using 23 different stops in very different sort of land areas from 7 a.m. until sundown. And MARTI measures surface temperature, so a little bit different than land surface temperature, the actual surface temperatures, air temperature, and that mean radiant temperature, that measure of thermal comfort. And then the last thing we did was run microclimate simulations. So the field observations are just point data in time, but the microclimate simulations allow us to interpolate all the surfaces in the neighborhood. And we used NVMet software to do that, and simulated the same three variables: surface temperature, air temperature, and mean radiant temperature. And then finally, we ran regression models to examine the predictive power of different climate variables. So first, the first kind of headline from our study is looking at the remote sensing data. Now, I want to explain a little bit more what you're looking at here. The top bucket in the first panel, the blue area, that is the first phase of this Savano development. And it is using sort of new urbanist design and has a lot more sort of green land features than this purple region, which was the second phase, in which all of the new urbanist design principles were dropped, and instead this neighborhood leveraged kind of building technologies, sort of increasing the R values of walls and good insulation and for windows, that kind of thing. And then the last one in green at the furthest south neighborhood is just a plain suburban sprawl neighborhood with no sustainability goals. And we repeated a study that had actually already done, but we updated it to be the same time period as this study, and found similar things, that Savano, the first phase, the new urbanist phase, was greener. It had, you can see in the bottom left panel, much higher albedo, and that translates into cooler temperatures. And when you do the LISA analysis of autocorrelation for clustering, you see this big blue blob where the cold spots are. So essentially this new urbanist neighborhood is much cooler than the surrounding neighborhoods. And so the headline here is that Savano is able to cool the neighborhood, at the neighborhood scale, it is a much cooler microclimate than the surrounding suburban neighborhoods because it has more vegetation, higher albedo, and the most cold spots. But actually, if you look within this area, there's little variation in land surface temperature, and most of that is coming from this sort of desert edge effect. So the desert environment is just quite hot and causes some of these pixels to show up as really, really hot temperatures. And so if you look at the box here with the min and max surface temperature derived from remote sensing, and this is a 10 a.m. image that we're using, you see the minimum temperature is 37 degrees Celsius and the max is 44 degrees Celsius. Focusing though on our field and our simulated data, I'll direct your attention back to this box where I've repeated the remote sensing 10 a.m. image. If you look at what the surface temperature was at 10 a.m., not derived from remote sensing, but from field measurements, you see way more variation because hyper level land surface temperature is just way more sensitive to micro scale features in the environment. So at 10 a.m. we get a minimum land surface temperature of 10 degrees Celsius and a max of 55 degrees Celsius. And so I'll walk you through these charts. We're looking at diurnal trends. So what happened from morning through the afternoon and into the evening. And starting at the top, we're looking at air temperature. And if you follow the curve, air temperature is peaking in the late afternoon. And if you look at the box and whisker plots, you see the boxes are quite flat. And that means that there's little variation between all the different sites that we measured. And even when you look at the simulation, that is true. In the middle, we're looking at mean radiant temperature. And the diurnal trend is a little bit different. You do see kind of hotter temperatures in the midday, a little bit earlier in the day than air temperature, and that's what we would expect. But you also notice that the box and whisker plots get a lot fatter, especially during the morning and the late afternoon, saying that some places are just really hot places to be a pedestrian no matter what time of day it is. And we would expect that because we know that mean radiant temperature has a lot more to do with solar exposure rather than sort of the surface temperature and trends throughout the day. And then finally at the bottom, this bottom panel is just the surface temperature. And so surface temperature peaks midday, similarly to mean radiant temperature. And here we looked at different surface types to get an idea if asphalt, concrete, grass, and gravel varied. And we did find that surface temperature in the middle of the day was moderately cooler in the grass and the vegetated area versus the impervious surfaces. Okay, then we looked at the predictive capacity of remotely sensed information. So the remotely sensed derived estimate of land surface temperature. Does it predict our simulated temperatures of land surface temperature, mean radiant temperature, and air temperature? And we found that it's provides a weak estimated of these simulated temperatures. So these regional sort of satellites are giving us a weak signal of what's happening in local, hyperlocal conditions. So sort of moderately good news is that it was a better predictor of MRT than air temperature and land surface temperature. So if you care about thermal comfort, it was a little bit better of a predictor. However, the strongest predictors were negative relationships because remember, it's a 10 a.m. image, so you get these negative relationships in the late evening time. And so that's one thing to keep in mind is that our satellites can't give us that sort of daytime variation in temperature, which becomes important when you are planning interventions. Shortwave, this is showing you shortwave radiation, and that's sunlight exposure. So sunlight exposure is a better predictive of these hyperlocal temperature conditions. So as expected, we saw a very strong relationship between that solar radiation, how much sunlight a site is exposed to, and the mean radiant temperature. But we also saw that it was predicting variation in midday surface temperature. And I would just direct your attention, this is an image, there are lots of images like this that you can find of showing the sort of a camera image of surface temperature in an urban environment. And in this case, you can see very clearly the tree shade is augmenting the surface temperature compared to the part of the street that is not covered by trees. So in hyper-local conditions, that sunlight is a good predictor of surface temperature as well. And again, air temperature, probably because there's so little variation at this really, really fine local scale in air temperature, we don't get much predictive capacity in either model. Finally, we looked at what urban land features predict this remote sensing derived land surface temperature and which predict MRT, or what the relationships were there. And so if you're looking at remote sensing imagery of near land surface temperature, you get stronger relationships with the built environment, right? Because it's more tied to the surface material than is MRT. But especially you get strong relationships with land cover variables, and that's versus sort of three-dimensional variables. So things like how much building cover, how much impervious surface, and the percent of tree cover are predicting what the land surface temperature is using remotely sensed models. But if you use MRT, you get weaker relationships overall with the built environment because it's more strongly tied to that incoming solar radiation. You get stronger relationships with morphology variables. So unsurprisingly, three-dimensional variables, things that could cast shadow or shade, are more predictive of MRT than just the surface cover materials. And so things like the percent trees, again, were important. But also mean building and tree height also were predictive of variation in mean radiant temperature. So what is the consequence of this for local planning? What would I say to local planners based on this study? Well, first of all, to the urban climate scientists in the audience, I know that none of this is perhaps groundbreaking to you. You probably know that this is how urban climate works, but in my experience, having tangible physical examples of how in practice these different climate variables are playing out is important for communicating at a sort of a planning and policy level. So what would I say? First, it's important to define the heat goal. Urban heat island mitigation and improved thermal comfort are not necessarily synonymous, and not always the same interventions won't necessarily address both. So it's very important to set out and say, is this an instance in which we want to mitigate regional heat island, or is this an instance where we're concerned more with hyperlocal sun exposure? The second takeaway is that it's really important to specify temperature type. So, when you read through, as I have lots of heat plans, you see that things like Celsius versus Fahrenheit are rarely differentiated. Sometimes just temperature numbers are put forth. So I would go one step forward and say, we also need to, just as we say Celsius versus Fahrenheit, we also need to say, are we talking about land surface temperature? Are we talking about LST? Are we talking about MRT? Because they measure different things, and so it's really important to be specific. And especially be cognizant of what remote sensing can estimate. It can estimate this land surface temperature, but it can't describe everything, like diurnal variation, morning versus night. And it can't describe air temperature, and it can't describe mean and radiant temperature. And finally, because of the differences throughout the day in these different temperatures, it's important to ask when and how space is used. So interventions perform differently throughout the day. So, you have to think about when a specific group is going to be using a space, and then decide, maybe this is, a rooftop would be a fantastic place for cool roofs for urban heat island mitigation, but maybe a playground would be better suited for a shade intervention. So with that, I want to say thank you and show my stripes, and give it back to the audience for questions. Thank you.
Wonderful. Thank you, Kelly. As you've seen, we've kind of gone from really up in the atmosphere down to the ground and then back to the middle. So we've really traversed some vertical boundary layers here to bring it back to Aldo's original presentation. One question, Joshua. Marty seems to measure thermal comfort, discomfort in arid climates, but what about climates with high levels of humidity? Does Marty already account for this in measurement in some way? So just a little question about the cart.
Yeah. Yes, Marty measures humidity. And in fact, we had a great example. We took Marty out in the East Coachella Valley recently to what is a very arid environment, but a place that had a park intervention. And Marty can sense that it is much more humid. And to bring it back to what Aldo was talking about humidity making sweating less effective, it feels quite hot. So Marty is going to account for differences in humidity.
Great. So as we wait for any other additional questions, I'd love to bring it back kind of the full group. But before we do that, Kelly, curious about a question about regulatory levers that might be helpful to address some of these interventions. You got at that in the last slide. So just thinking more from a maybe policy regulatory perspective, what comes to mind when you think about these different ways to measure heat and potential regulatory approaches?
Yeah, well, urban heat governance, as you know, is really in its infancy at this point. We don't have many institutions. And again, our keynote panel, they were talking about, California would like to pass legislation, which I'm very supportive of, to do heat coordination. And I think it'd be important to get all these groups talking so that I think what can happen is that, because there's not the same level of sort of governance and literacy around heat, is that different types of heat phenomenon can be conflated. So it's really easy to say, oh my gosh, we've really reduced, based on remote sensing analysis, we've seen this huge reduction in surface temperature, and then to apply that knowledge at a really hyper-local scale. And then you can do an intervention that's not scalable, like that needs a certain amount of surface coverage to generate the results that you see in regional studies. So I guess in terms of the policy levers that we need is probably not thinking about urban heat island mitigation necessarily, but disaggregating that into mitigating urban heat locally. And I also, one of my pet peeves is talking about urban environments as extreme heat adaptation versus mitigation. I think actually our urban environments produce, I've called it urban heat pollution. And so I think that calling it mitigation or calling it adaptation to extreme heat really does a disservice and really lets people who develop without trees in really impervious ways off the hook for contributing to urban heat.
Fair point. Thank you. Dave is asking about the ability or feasibility of being able to reduce UHI. Is that feasible? Is that real? And that, yeah, you can kind of get that question of reducing. Is it reducing UHI? Is that a feasible goal?
Oh yeah, well, I would direct you to a great paper on that. Martilli et al. Is urban heat island relevant for, I forget the rest of the title, heat planning. And they discuss this very question in detail. I don't think urban heat island is bad. I just think it's a signal, and it's a regional signal that, I think we should have the overall goal of reducing the thermal burden produced by the built environment. I do think having regional greening programs is a good goal. I just think it's a different goal than trying to protect human bodies in the neighborhoods where they are moving about.
Yeah, interesting. So maybe that's a great segue into a broader conversation that tries to bring together all of the speakers that we had today. I'd love to get your thoughts on each other's presentations to see if there's overlaps, connections from things that are numerical and model based to things that are on the ground and experiential, to potential ways of being able to characterize health impacts from these different ways of measuring heat. So I'd love to just pose. I have several questions I'd love to pose, but let me just turn it over to the actual presenters. and get an idea for any comments that are coming up in terms of the interaction or intricacies across these different presentations. Anything coming to mind, Edith or Aldo, Kelly?
Well, there's definitely overlap between the street trees and different albedo surfaces, technologies used to reduce heat in urban environments. But yeah, it's interesting, the contribution brought by everyone participating in this discussion, and because the whole picture is much more complex than sometimes it is depicted. There are so many aspects of these problems that need to be taken into account, and yeah, talking about feasibility, probably sometimes it's not really a near goal to reach. But yeah, it was very interesting to learn about all this, the implications.
Maybe I'll just present it as one notion of, I know we brought up the notion of geography several times, and many of you are geographically inclined. So one of the things that often comes up is the relationship between microscale interventions and macro scale interventions when you're thinking about heat. And the things that numerical models and WRF can do potentially is to create these kind of spatially and temporally expansive outputs, whereas there's a lot of work happening at that hyper local scale. So I'm curious as to your thoughts about when you're talking to practitioners who are trying to address heat in an urban setting. Like, do you have thoughts about where to begin that work? Is it at that very hyper local scale, as with pilot projects and scaling up, as Edith suggested, or maybe as Aldo or Kelly suggested, like, or as Aldo suggested at the regional level, or even as Kelly suggested at the neighborhood scale? Are there thoughts that you might have on that?
Well, I think that when you're talking about the most vulnerable neighborhoods, you need to start at the hyperlocal scale, and you need to protect, like literally just protect the bodies that are more at risk. But I think that it's an iterative process. I think we need the regional scale models to direct resources. I think that's a reality, and I think it's super critical. But I think that when it comes to day-to-day lives and vulnerability to heat, which is incredibly inequitable, we need to do the things that are going to prevent people from overheating and getting sick and dying.
I would agree with what you said, Kelly. I would also add, though, that sometimes we just have to go where the opportunities are when it comes to, following where the funding is or where the opportunities are in terms of partnerships. So to your question, Vivek, my thinking goes to, especially given the fact that we've revealed that sometimes there are unintended consequences, there might be benefits in one sort of application and maybe less so in others. And until we get really collectively smart about that, my advice, I think, to practitioners and policymakers is to be as multi-benefit as possible and as sort of future-proofed and, no regrets as possible, given at least what we know so far about this very complicated topic.
Any closing bits on that, Aldo?
Yeah, no, I agree, and I would like to draw on Edith's comment. It's like change happens at all scales, but intervention cannot always address that change at all scales. It's like global change is not addressable by cities, by municipalities, and changes that happen at the global scale are still felt at the micro scale, at the neighborhood scale. So it's like, it's of course you do what you can and based on opportunities, but I think it's also useful to keep the broader image always in mind, because it's like for population estimation projections, it's like global climate change will affect migration patterns, and so like what today is seen as just a global problem tomorrow can become a local problem because populations are displaced. And so a neighborhood that was like a lower density neighborhood today, tomorrow can become a high density neighborhood. And again, also I've seen comments about what kind of trees and vegetation species to use in a specified location. And if climate change, regional climate changes, also the adaptability and the way you can use plants in a specific location changes, because native species are not necessarily the most adapted ones anymore with global change and regional change. So it's a matter of scale too, and so it adds complications to the problem.
Thanks, Aldo. Thanks, Edith. Thanks, Kelly. We're right a little bit past time, so I want to thank again this preeminent group of folks who are just really at the cutting edge of a lot of this work, and really encourage you to follow them and their work. I want to give you a little bit of I want to thank the audience, of course, for the questions and participating. Just give you a heads up, at 3:30 Pacific Coast time, we're going to have another 4 sessions. One is the effects of temperature on behavior. Then there's adaptation at home, consumption, building code, and insurance. And then there's quantifying and minimizing water quality impacts. And the 4th session, concurrent session, is integrating climate and transportation planning. All totally right in the wheelhouse of, I'm sure, many of your interests. So please stay tuned. And thanks again, presenters. Thanks for joining.
Thank you for moderating.
Thank you, Vivek. Yeah.
Thanks, everybody.